Order of an element. The order of an element A of a group G is the least positive integer m such that a power m equal to e. So observe the definition. A is an element of G. Now I need order of this element. This order is equal to m if a power m equal to e. This m is least positive integer. This m is least positive integer. If there exists no such integer, that means if it is not possible to find an integer m such that a power m equal to e, we can say that a is of infinite order. The order of an element A is denoted by order of A, and it is read as order of A. Here one note is there. Observe that one. For any group, the identity element is the only element of order 1. That means if in any group order of identity element is equal to 1. Now we can find orders of each element of fourth roots of unity. So observe, the fourth roots of unity means it is 1 minus 1 I minus I. This set is a group with respect to multiplication, and also identity element is 1. Now I need order of 1, order of minus 1, order of I, order of minus I. Here 1 is the identity element, so order of 1 is 1. Now I am going to find out order of minus 1. Minus 1 power 1 is minus 1. So this is not an identity element. Next, check by taking power as 2. Minus 1 power 2 is 1. So this is the identity element of G. Therefore, we can easily say that order of minus 1 equal to 2. Next, order of I need. For this, I am going to check whether I power 1 equal to identity element or not. We know that I power 1 is I itself. That means we are not getting identity element. I power 2 equal to minus 1. So this is also not an identity element. I power 3. I power 3 means I square into I. We know the value of I square, that is minus 1 into I. That means we are going to get minus I. This is also not an identity element. Next, we check 4 as power for I. I power 4 means I square into I square. This is nothing but minus 1 into minus 1. That is 1. So when we take power as 4, we are getting identity element. Therefore, order of I equal to 4. Next, we want to find out order of minus I. Minus I power 1 equal to minus I. This is also not an identity element. Minus I power 2. Negative square is positive. I square. I square is minus 1. This is also not an identity element. Minus I power 3. That means minus I whole square into minus I. We know the value of minus I whole square, that is minus 1 into minus I. So this is nothing but I only. That means we are not getting identity element. Minus I power 4, that is minus I whole square into minus I whole square. We know the value of minus I whole square, that is minus 1 into minus 1. Minus into minus is plus, 1 into 1 is 1. Here you can observe we get identity element. Whenever we get identity element, then power is the order for the corresponding element. That means order of minus I equal to 4. So now we have all orders of elements of G. Order of 1 is 1. Order of minus 1 is 2. Order of I equal to 4. Order of minus I equal to 4. Next, we move on to another example. Find the orders of the elements of the multiplicative group G equal to 1 omega omega square. This group is called cube roots of unity. Here the binary operation is multiplication. We know that 1 is the identity element for this group. So order of identity element is always equal to 1. Now I need order for omega. So observe omega power 1 equal to omega. So identity element we are not getting. Check by taking 2 as power for omega. Omega square is omega square only. So we didn't get identity element. Omega cubed equal to 1. So 1 is the identity element. Whenever we get identity element, the order is power only. That means order of omega equal to 3. Next, omega square. Power 1 is omega square only. Omega square whole square is omega power 4. Omega power 4 can be written as omega cubed into omega. We know the value of omega cube, that is 1. 1 into omega is omega. By taking 2 as a power for omega square, we are not getting identity element. Again, by taking power as 3, omega power 6, that means omega cubed into omega cube. Omega cube is 1. 1 into 1 is 1. So we are getting identity element. So order of omega square equal to power, that is 3. Now we have orders of 3 elements, that is order of 1 is 1, order of omega is 3, order of omega square is 3. Find the orders of the elements of the group G equal to Z4, plus 4. So Z4 is nothing but 0, 1, 2, 3. Here the operation is plus 4. So identity element is 0. Order of identity element is 1. Next, I need order for 1. For that, 1 plus 4, 1 equal to 2. This is the remainder when 2 divide with 4. Again, 1 plus 4 plus 4, 1. 3 is the remainder when divide with 4. 1 plus 4, 1 plus 4, 1 plus 4, 1. Adding these ones, we are getting 4. 4 divided with 4, remainder is 0. That means here we are getting the identity element 0. So, order of 1 is 4 because here we are using 4 ones. Next, I need order of 2. For that, I am adding 2 2's. Then we are getting 4. 4 divided with 4, remainder is 0. Next, 3 plus 4, 3. This is identity element. That's why order of 2 equal to 2. So 3 plus 3 is 6. 6 divided with 4, remainder is 2. So we didn't get identity element. 3 plus 3, 3 plus 4, 3. This is equal to 9. 9 divided with 4, remainder is 1. This is also not an identity element. So 3 plus 4, 3 plus 4, 3 plus 4. So addition of these 4 3's is 12. 12 divided with 4, remainder is 0. So here I am getting identity element. Therefore, order of 3 equal to 1, 2, 3, 4. Here one note is there. Observe that in the group z, plus of integers, every element except identity element is of infinite order. That means we cannot get 0 as power of multiplicity of any integer. That means if we add 1 plus 1, we are getting 2. But we need identity element. That's why similarly 1 plus 1 plus 1, 3. This is 3. This is also not equal to identity element. That's why we can easily say that in the group z, plus of integers, every element except identity 0 is of infinite order. That means order of 1 equal to infinity, order of 2 equal to infinity when we consider z, plus as a group. In the multiplicative group of positive rational numbers, every element except the identity element 1 is of infinite order. For example, take 2 by 3. This is a rational number. Here, if when we take q, cross multiplication as a group, 1 is the identity element, then 2 power any positive integer is equal to 1. That means here we didn't find positive integer such that 2 power 3 power positive integer equal to 1. That's why the order of 2 by 3 is infinity. We cannot find the positive integer m such that quotient number power positive integer equal to 1. Now we move on to properties related to order of an element of a group.